Hi, I'm Simon Whitting. I'm the Equipment and Observations Officer for Astro and I'm a second year Physics and Astrophysics student here at the University of Birmingham. I'm here to give you some information on what the night sky will look like for the next few months. So starting out in October, the first event listed here, the peak of the Orion's meteor shower, technically already happened about a week ago. But if you're absolutely desperate to go out and spot a meteor shower like right now, then it's still around until early November. So that will appear to radiate from the constellation of Orion, which very easy to spot, very distinctive, got a big belt of 3 stars in a row in the middle. There'll be another meteor shower peaking in the next few days, the Southern Taurids. Unfortunately, that one will almost certainly not be visible because the moon is almost full and it's a fairly minor shower to begin with. The full moon, which will be on the 31st, is a blue moon, which means it's the second in a month. The first is on the 1st of October. This is a figure of speech. It's not actually going to look blue. But if you ever wanted to know what once in a blue moon meant, now you know. Uranus will also be at opposition on the same night, which will mean that it's the closest to the Earth and therefore the most visible that it's been in a while. Unfortunately, again, the moon will probably blot it out quite a bit, but if you still want to try spotting it, you're probably going to need at least a set of binoculars, if not a full telescope, because it will be too dim to spot with the naked eye. Moving into November, there'll be another planet visible. This time it's going to be Mercury on the 10th, and it'll be at its greatest western elongation, which will mean that it will be visible just before sunrise in the low eastern sky above the horizon, and this will look to be visible to the naked eye. There'll be another meteor shower peaking on the 11th and the 12th. This will be the Northern Taurids, and if you want to find it, down here we have the constellation of Orion I was talking about before, and you see the belt here. If you follow it up diagonally and keep going until you pass Aldebaran on the side here, then you ought to reach where the Northern Taurids will radiate from. This is a fairly average meteor shower in terms of density, but it's famous for having above average number of bright fireballs, so if you manage to spot any meteors from this, there's a good chance that they'll be very visually impressive. There'll be a new moon on the 15th, and there'll be another meteor shower peaking on the 16th and 17th, the Leonids. This one's alright again, but thanks to the sky being pretty dark, it ought to be quite easy to spot. So if you want to find the Leonids in the sky, here we have Ursa Major. I like to think of it as a Big Dipper, but if you follow the side of the saucepan down that way, you can find the Leonids. Or if you know the constellation of Leo, you can just find it that way instead. That's a lot easier. And there'll be a full moon on the 30th. Finally, in December, we have the Geminids, which is, a lot of people think this is the best meteor shower there is, and frankly, I agree. It's really impressive. It's going to have roughly 120 meteors per hour at its peak, and they're very bright and multicoloured when they come down. So if you want to find that one, then either find the constellation of Gemini, if you know it already, or the way for astronomical beginners, I suppose. Here we have Orion's belt again, but if you follow it up perpendicularly this time and past Betelgeuse, which will be very obvious because it's quite red at the moment, then keep following it up quite a ways until you find here, and hopefully this meteor shower is intense enough that you need to look very hard to find it. It'll also be during the time when the moon is almost new, which means that the sky will be very, very dark. So this is going to be a good year for the Geminids. On the 21st is going to be the winter solstice, which will mean that it's the shortest day and the longest night. And this is a good timing because we're also going to have a great conjunction, which is a conjunction of Jupiter and Saturn. This is really rare, actually. It happens once every 20 years. So not like a once in a lifetime event, but definitely once in a few decades. And this is going to be, the last one was in 2000, that's going to be in 2040, and so if you want to spot this one, then you're going to have to make sure you stick around sunset on the 21st, and look to the southwest just above the horizon, and Jupiter and Saturn will be very close. They'll appear as like a single double planet like that's shown here, and they'll be around for a few hours. This is also good news if you want to spot either Jupiter or Saturn separately, just generally at the moment, because the fact that they're in conjunction this year means that they're both very bright and visible separately for the next few months coming up to this in December. So if you want to get a good look at those with your telescope, now's a good time. Finally, we have the peak of the Earth's meteor shower on the 21st and 22nd, which will be a fairly minor shower, but the moon will set around midnight, even though it's going to be well on its way to being full. So the sky should be fairly dark. And if you want to find that, then either you find Ursa Major, the saucepan again, and follow the bottom diagonally this way, or you can find Ursa Minor, which is, the little saucepan, and that'll radiate from around there. And there'll be a full moon, the last one of the year, on the 30th. Okay, so we have a highlight object now. Those of you who come to these talks before might recognise this one, but it's an oldie but a goodie in my opinion. The Milky Way is a great thing to try and spot, especially this time of year. It's kind of hard to see in the city or anywhere with light pollution, but if you can find somewhere that's dark, then it's amazing to try and spot on a winter night. And yeah, some facts about our galaxy here. We have a lot of stars, slightly less, but still a lot of planets, and we have a big black hole in the middle. Don't worry, we're not going to fall in. And it's quite big and not very thick, so it's big disc-shaped. So here we have a summary slide. If you want to take a photo of this or a screenshot to look up this stuff in your own time, feel free. And that's it. So hope you enjoyed this talk, and moving on to the next one now. Thank you.
Good evening and welcome. Thank you for attending the Astro in the City. I'm a second-year PhD student at the University of Birmingham, and I work on the lives of very heavy stars that could form into black holes and could eventually become gravitational wave events. Normally, during the Astro in the City, we talk about something that's related to the research that is done in the University of Birmingham. But now we thought we'd do something slightly different. We're going to talk about the great debate in astronomy. This debate tried to answer two questions. First, how big is the universe? Second, what are spiral nebulae? Today we know the spiral nebulae are actually spiral galaxies, just like our own Milky Way. But back then that was not known. It was not known how far away these objects are, how big they are, and whether they belong to our Milky Way or not. This debate happened between two American astronomers, both working in California, Harlow Shapley and Heber Curtis. The debate happened in 1920, April the 6th, at the Smithsonian Museum of Natural History. In 1920, the world was a very different place. We didn't have a proper theory of stellar evolution, and we did not know about the nuclear fusion that was going in the center of the stars. We also thought the universe was static, and we had way worse telescope back then, and we only had optical astronomy. We didn't have radio, infrared, or X-ray observations. Imagine that you are in 1920 and you're looking at the night sky. You're looking at the Andromeda constellation, and above its bright star you notice a fuzzy patchy object. How would you determine the size of this object, how far away is it from us, and whether it belongs to the Milky Way? These were the questions that Shapley and Curtis wanted to answer in their debate. However, in order to understand how they wanted to tackle these questions, we need to understand what was the view of the universe in the 1920s. So in order to understand this, let's review the scientific progress made in this area, starting from the 18th century up to 1920. This brings us to Thomas Wright, an English astronomer, who, in order to explain the structure of the Milky Way, as is seen in a clear night sky, he proposed that all the stars, including our Sun, are in between two concentric shells. This way it can be understood that in one direction we see more stars than in the other. Immanuel Kant, the famous German philosopher who was inspired by Thomas Wright, went one step further. He proposed that the little fuzzy patches that can be seen in the sky could be possibly other universes. Therefore he coined the term island universes. William and Caroline Herschel, famous astronomers, built the Great 40-foot telescope in 1789, which was the biggest telescope in the world at the time. They did this in order to create a map of the universe for the first time ever. They had three major assumptions. First, they neglected the interstellar dust absorption. They assumed that the stars are uniformly distributed in the universe, and they also assumed that all the stars that are in the universe can be resolved by their telescope. Then they created a map by counting the stars all over the sky. We can see that they concluded that our universe has a flattened structure just like our Milky Way, which should not come as a surprise since all the stars that they could observe actually were part of the Milky Way. They also concluded that the Sun is very close to the center of the universe. Jacobus Kapteyn, a Dutch astronomer, also created a map in 1996 using photography. He used more sophisticated methods than Herschel. He measured the proper motion, the radial velocities, magnitudes, and spectral types of the star. He also neglected the internal dust absorption. Using these measurements, he was able to create a map again. However, this time he was also able to determine the dimensions of the universe. He concluded that the Milky Way is 55,000 light years long across and 10,000 light years tall. And again, he also concluded the star must be in the center of the universe, or at least very close to it. Charles Messier, a French astronomer in the 18th century, observed fuzzy patchy objects in the sky while he was looking at comets. Therefore, he decided to create the first catalogue of these objects, which I'm going to refer to as nebulae. This catalogue contains 110 objects and they all have different origins. They contain galaxies and globular clusters. Globular clusters are a spherical collection of stars that orbit around galaxies. In the catalogue there are also open clusters, one supernova remnant, diffuse nebula, which are like star-forming regions, and planetary nebula, which are the star remnants of intermediate and low mass stars. In the time of Messier, it was not possible to distinguish many of these objects from each other. It was William Parsons, a very rich English and Irish astronomer, who managed to show that some of the objects in Messier's catalogue have a spiral structure. He did this by building the largest telescope in the world at that time in Ireland with an aperture of 1.83 meters. In the 19th century there was another important achievement. The astronomical spectroscopy was born. So what is spectroscopy? Just think of Newton, who used a prism to break up the sunlight into different colors. This is what does. We basically take the light and we decompose it according to its wavelength. There is another important thing to note. If you take the spectrum of a hot, dense object, then you would get the so-called blackbody spectrum, which is continuous. If you take the spectrum of the diffuse gas, then you would get the so-called emission spectrum, where you see peaks at certain wavelengths. Where this wavelength occurs tells something about the composition of the gas. If you would take the spectrum of a star, you would typically get something called the absorption spectrum, which is a blackbody spectrum with absorption lies in it, aka a troughs. Again, where these troughs occur tells something about the composition of the gas in which these blackbody-like objects embedded. This brings us to William Huggins, who often considered the pioneer of the astronomical spectroscopy. He was the first one who managed to distinguish between certain Messier objects by studying their spectrum. He managed to show that, for example, the Orion Nebula showed emission spectrum, which means that it was a gas cloud. On the other hand, Spiral Nebula spectra was very similar to that of the stars, because they had absorption spectrum. Julius Scheiner, a famous German astronomer, for example, also showed that the spectrum of the Andromeda is very similar to that of the Sun. This suggested the spiral nebula might consist of stars. Let's move our attention to a different topic. How to measure distances. Henrietta Leavitt, an astronomer at Harvard, studied the so-called Cepheids, which are variable stars in the small Magellanic Cloud. She discovered that there is a relation between the Cepheids' pulsation period and their luminosity. So what these stars are doing, that they basically are pulsating radially. The pulsational periods are related to their luminosity. This means that these stars are standard candles, which means that we can use them to directly measure their distances. So how do we do this? Imagine that you have a light bulb which has a power of 100 watts. Looking at its brightness, you can figure it out its distance from you, because the brighter it seems, the closer it is. This is the idea behind the Cepheids too. Since you can measure their pulsation period, using the Leavitt's luminosity period relation, you can determine their luminosity. Comparing this to the measured apparent brightness, you can actually work out how far away these objects are from you. Let's discuss another important observations that greatly influence the great debate. These observations were made by Vesto Slipher, an American astronomer working at the Lower Observatory in 1912. He noticed that the absorption line for many spiral nebulae were shifted to lower frequencies. He realized that this phenomenon is caused by the radial velocity of these objects. In order to understand this, think of the Doppler effect. Imagine a fire truck that is approaching you. As that's happening, its sounds will sound more high-pitched, which means that the sound shifted to higher frequencies. However, as it going away from you, the opposite happens, and the frequency of its sounds will decrease. Vesto Slipher managed to relate the radial velocities of the observed spiral nebula to the shifts that he observed in the absorption lines. He concluded that the velocity of these objects were quite high, and quite often they were above the escape velocity of the Milky Way, which meant that they are probably not gravitationally bound to the Milky Way. We finally arrive at 1920, April 26, the date when the great debate happened. It was organized by George Ellery Hale. He wanted to organize something that would be interesting for both astronomers and non-astronomers as a part of the meeting of the National Academy of Sciences. The original topic would have been special relativity. However, George Ellery Hale thought that that topic had already been discussed too many times and the audience would find it too boring. So instead they chose the topic would be the size of the universe or the nature of the spiral nebulae. Therefore, they chose the main debaters to be scientists who recently published papers in this topic. Therefore, they chose Curtis and Shapley. The debate consisted of 2 talks, each 40 minutes, which were followed by discussions. Shapley's main point was that the universe is larger than as suggested by captains, and the Sun is not in the center of this universe. At the same time, he thought that the spiral nebulae are part of the Milky Way. On the other hand, Curtis' main point was that Kapteyn's model for the Milky Way is correct. But he thought the spiral nebulae are not part of the Milky Way, and he thought that the spiral nebulae are similar objects to Milky Way, that is, they are galaxies. First, let's look at Shapley's arguments in more detail. In his 1980 paper, he measured the distances of globular clusters around the Milky Way using RL Lyrays, although he thought that he was using Cepheids. He assumed that the globular clusters must be distributed around the Milky Way symmetrically, as it is shown in the plot that is included. He found that there are a roughly equal number of globular clusters below and above the plane of the Milky Way. However, he found significantly more globular clusters in the direction of Sagittarius, which is the center of the Milky Way. From this, Shapley concluded that Kapteyn's model for the Milky Way must be wrong. This is shown in the figure on the right, where we plotted Kapteyn's Milky Way as a disk, and the little circles denote the positions of the globular clusters as measured by Kapteyn. Shapley suggested that Milky Way's dimensions must be larger than computed by Kapteyn, and furthermore the Sun cannot be in the center of the Milky Way. Shapley estimated that the Sun is about 50 kiloparsecs away from the galactic center, which is about 49,000 light years. He also estimated the Milky Way to be 100 kiloparsecs long across, which corresponds to about 3,300,000 light years. In his calculations, he assumed that the absorption by interstellar dust can be ignored. Furthermore, he thought that the spiral nebulas belong to the Milky Way. He based this on the measurements of Van Manen, who was a very famous astronomer at the time. He observed the Pinwheel galaxy for about 15 years, and he was trying to determine its rotational period. According to his observations, he estimated this rotational period about 0.022 arcseconds per year. This corresponds to 86,000 years. So if you assume that the spiral nebulae are actually galaxies and they have the same size as the Milky Way, then you can estimate the orbital velocity of a star that has the same separation from the galactic center as the Sun is. If you do the math with this rotational period, then you would get that the orbital velocity of such a star is about 3.6 times the speed of light. From this, Shapley concluded that the spiral nebulae must be a part of the Milky Way. Now, in order to appreciate how difficult it was to carry out those measurements that Van Manen did. Note that 0.022 arcsecond corresponded to a 0.01 millimeter change in the plate. The main point of Curtis' talk was that the spiral nebulae are not part of the Milky Way. His main argument was that in spiral nebula's edges he observed dark obscuring bands, just like as is shown in the photo for the Needle Galaxy. Similar obscuring bands can be also observed for Milky Way, so he thought that this dust can be found at the edges of all spiral galaxies. He furthermore did not think the Cepheids are reliable distance indicators, therefore he did not believe Shapley's results and thought that Kapteyn's model is more accurate. From this it follows that he also thought that Sun must be very close to the center of the Milky Way. During the debate, Shapley tried to find an explanation for the observed radio velocities of the spiral nebulae. He suggested that these might be caused by the radiation pressure of Milky Way. However, Henry Russell, a famous astronomer, quickly demonstrated that this is impossible using simplified calculations. He knew from measurements that the intensity of Milky Way corresponds to about 3.5% of the flux from a first magnitude star. Such a star is 1.2 times 10 to the power 11 fainter than the Sun. From this, he calculated how long it would take for the nebula to accelerate up to the radio velocities that are observed. From this, assuming constant acceleration, he calculated how much distance this nebula would have traveled during this time. He arrived at 1.6 times 10 to the power 10 parsecs, which was way more than was expected. There was another problem concerning novae and supernovae. These are both transient events that are observed for only a short amount of time. Novae and supernovae are two different kinds of events. Novae is caused by a white dwarf in a binary system accreting mass from another star. As the accreted mass is falling on its surface, it gets heated up, and nuclear fusion might set in. It could lead to an unstable runaway process which results in an explosion, which is observed as a transient event. On the other hand, supernova, which is far more luminous, it is caused by either a collapsing star or an exploding white dwarf. Novae can happen about 40 or 60 times a year in the Milky Way-like galaxy, whereas supernovae are way rarer. They happen about few times in a century. Because of that, during Shapley and Curtis' time, very little known was about supernovae, and they had no idea how luminous these events are. In 1895, a supernova occurred in the Andromeda Galaxy. Shapley assumed that it was a nova-like event, and because of that, he argued that the Andromeda cannot be too far away. Otherwise, it would imply that the event observed in 1895 had an extreme large luminosity. However, Shapley did not know that supernovas are indeed extremely luminous and they can outshine a whole galaxy. The other problem was that the number of nova events observed in the Andromeda was the same as in the Milky Way over a year. From this, Curtis inferred that Andromeda must be a Milky Way-like galaxy. Why else would a random place in the universe have so many nova events? In 1920, the outcome of the debate was inconclusive, and we had to wait until 1925 till we got an answer for one of the most important questions for the debate. Knut Lundmark and John Duncan observed the galaxy M33, and they discovered variable stars. Hubble got inspired this, and he started observing the Andromeda, where he managed to discover two Cepheid stars. He used these stars to derive the distance of Andromeda from us, and he arrived at a distance of 930,000 light years. It turned out that he used the wrong class of Cepheid stars, and today we know that the distance is actually 2.54 million light years. Even with his wrong value, however, it became clear that Andromeda is not part of the Milky Way, and in fact, it's another spiral galaxy, just like our own Milky Way. So let's summarize the outcome of the debate. In some cases, both the scientists were wrong, but in other cases, Curtis was right, and in our case, Shapley was right. So, concerning the position of the Sun with respect to the center of the galaxy, it turns out that Shapley was right. Today, the estimated distance of the Sun from the center of the Milky Way is about 8 kiloparsecs. Regarding the size of the Milky Way, none of them were right. However, Shapley was closer to the truth. The current estimated diameter of the stellar disk is about 200 kilolight years. Regarding the nature of the spiral nebulae, Curtis was definitely right. Andromeda and other spiral galaxies are not part of the Milky Way. About the usefulness of the Cepheids as distance indicators, Shapley turned out to be right. Even today, they are used in order to determine distances. Both were wrong about the significance of interstellar dust absorption. It is actually important when one wants to determine the distances, and probably this is the main reason why Shapley overestimated the size of the Milky Way. Regarding the correctness of Van Manen's results, Curtis was right to doubt those. So to conclude, let's just quickly summarize what we know about the universe and the Milky Way. Since the advent of radio and infrared astronomy, we learned a lot more about our Milky Way. We managed to determine its dimensions to a much higher accuracy. And we also know now that it has a central bar-shaped structure. Regarding the observable universe, we estimate that there are about 10 to the power 11 galaxies that can be found there. I'm showing you here a photo that was made by the Hubble telescope. By far, the most of the objects that can be seen here are galaxies. Keep in mind that the Hubble telescope has zoomed so much such that the observed sky patch is equal to the area covered by a grain of sand pointed against the sky. That concludes my presentation. Thank you very much for attending it, and we'll be happy to answer your questions. Thank you.